Hello everybody, Mike again, video number 4 on respiration. Here we go, link reaction over, and there it is, acetyl coenzyme A. There's the all-important acetyl group with it containing 2 carbons atoms. The coenzyme A is the carrier molecule. And we're now into the mitochondria, the matrix of the mitochondria, and that acetyl group is going to be added to this. It's a 4-carbon sugar called oxaloacetate. In doing so, the acetyl group, once bonded to the oxaloacetate, will produce a 6-carbon sugar called citrate. The coenzyme A carrier molecule breaks away and returns for the process of the link reaction to take more acetyl groups away from pyruvate, and so help to keep the Krebs cycle to continue. Now then, what do we need to learn about the Krebs cycle? It literally is a cycle of intermediate sugar being turned from one to another. And during the process, hydrogen atoms are removed. Substrate phosphorylation also occurs. What do we have to learn in terms of names of sugars? Well, no more. The only ones you need to know is oxaloacetate and citrate. What I would learn though is the number of carbon atoms in each of the sugars. Now we've got a 6-carbon sugar there, the citrate, and it then changes to another 6-carbon sugar there. So if we try and remember a number which will help us, 6, 6, they're the 2 6-carbon sugars. We've got it's going to be turned to a 5-carbon sugar and then a 4-carbon sugar. So if I go back to the number 6654, 6654. Now, what have we then got? We've got 1, 2, 3, 4 more carbon sugars. I'm going to put a bracket and I'm going to go 1, 2, 3, 4, and then I'm going to put a bracket around it. So if you can remember, it's like a telephone number, isn't it? 6654 brackets, 4, 4, 4, 4, close brackets. If you can remember that, then on a rough piece of paper in the exam, you could just draw a circle, start with citrate, there's your first 6, and then that's going to have a name to it. That's going to be citrate, and then start listing the numbers on a rough piece of paper. 6654 brackets, 4, 4, 4, and then it's the last number 4. That's going to be the oxaloacetate, and then you can actually see the cycle formed. Oxaloacetate. Now then, we can now start adding muscle to the skeleton, muscle to the bones now. Start with that second number 6, 6-carbon sugar. It's been turned to a 5-carbon sugar. Well, there's only one way that can happen, and that's if carbon dioxide breaks away. That will remove a carbon atom from that 6-carbon sugar, and that's called a decarboxylation. Decarboxylation reaction. Right, now then, try and remember this. Whenever that occurs, we're going to get the reduction of NAD. So there's going to be a hydrogen atom lost at the same time, like that. And we're going to get NADH. I'm going to put plus H plus. The reason for that is that the NAD molecule can actually receive 2 electrons, one from each hydrogen atom, and that's why they put that. Right, let's have a look. We've got a 5-carbon sugar turned into a 4-carbon sugar. Let's do it again. Another decarboxylation reaction will get the 5-carbon to a 4-carbon, and we're going to have another reduction of NAD to NADH, like so. Excellent. Now then, this is good. We've so far formed 2 reduced NAD molecules. Each of those will go on to oxidative phosphorylation. Each of those on average will produce 2.5 ATP molecules by oxidative phosphorylation. The next stage is where substrate level phosphorylation can kick off. We've got a molecule which is very similar to ADP. It's called GDP, and that can pick up a phosphate group from the matrix and turn to GTP. That's an energy rich molecule, very similar to ATP. When that first 4-carbon sugar there changes to a different 4-carbon sugar. Now then, the next reaction is 4-carbon again to 4-carbon, but this allows a carrier molecule called flavine adenine dinucleotide, FAD, to pick up 2 hydrogen atoms, FADH2. Slightly different to NAD, the production of FADH2 will only produce on average 1.5 ATP molecules during oxidative phosphorylation. Then what we got? Let's have a little gap, and then finally we're almost there, back to oxaloacetate again, and then we've got our final reduction of NAD to NADH here. Now then, let's just have a little think. We've got our complete cycle now. Let's just have a little think. We started with 1 hexose sugar. The hexose sugar was broken down and eventually formed 2 pyruvate molecules, and that means that 2 acetyl-CoA molecules will enter the Krebs cycle. So we're looking at 2 turns of the Krebs cycle. Starting with reduced NADH, each one, I'm going to change the colour of my pen, each one will produce 2.5 ATP molecules on average. So here goes. 1, 2, 1, 2, 3. 3 times 2.5, well, I better work this out actually. 3 times 2.5 is, we've just made, with 1 turn of the cycle, 7 ATP molecules just from NADH. Now, hang on a second, look at this bad boy. We've got FADH2. Now that, in oxidative phosphorylation, will produce 1.5 ATP molecules. 2 turns of the Krebs cycle, we're looking at 3 ATP molecules. We add that to the number 7. Okay, I can easily add that up, he says with his Yorkshire accent. 3 plus 7 is 10 ATP molecules, now produced by oxidative phosphorylation. And finally, hold on a second. Whoa, we've got a GTP molecule, which is the equivalent of ATP in terms of currency. 2 turns of the cycle will produce 2 GTP, and so if you like, we could call it an ATP, and we could add 2 ATP to the cycle. So we're looking at 12 ATP molecules, aren't we? Just from the Krebs cycle in that process. Excellent. That's the end of video number 4. And I'm going to do a separate YouTube video on oxidative phosphorylation. Thank you for listening. Thank you very much. Thank you. See if I can turn this off. Hang on, I'm coming. Here we go. So we turn that.